For the training series on various studies using MiPower software, we are covering short circuit study in this presentation. We can study the effect of series faults and shunt faults in the power system using MiPower software. The prerequisites for conducting short circuit study are the GUI file or the single line diagram and the MDB file, the database. The inputs required for conducting short circuit study are the network parameters, which include bus voltage levels, then transmission line parameters, transformer impedances, motor data, etc. Then generator transient direct axis reactance XD dash or subtransient direct axis reactance XD double dash. Then vector groups of transformers, breaker rating of the circuit breaker which we have connected in the system. The outputs from the short circuit study are fault MVA, fault current, post fault bus voltages, fault contribution from different volt elements, then the adequacy of different breaker ratings. Now the features in SCS are the different types of faults we can simulate, that includes shunt faults and series faults. We can conduct three-phase to ground fault, single line to ground fault, line to line fault, double line to ground fault, single phase open fault, two-phase open fault. Also we can conduct fault on different buses, different transmission lines and different traction loads. The different reporting options available are standard, customized and HTML report, as we have seen in the load flow analysis.
Now we are going to conduct fault analysis for this network. For that, we have to click on Solve Short Circuit Analysis, give a case number and case name, and then click on Study Info. So the different faults are three-phase to ground fault, single line to ground fault, line to line fault, double line to ground fault, single phase open fault, two-phase open fault, and three-phase and SLG fault, one after the other. So here we can see different types of shunt faults and series faults. We have the option to conduct fault on bus, fault on line, and fault on traction load. For time being, we'll conduct three-phase to ground fault on all bus. So we have to select the fault type as three-phase to ground fault and element type as fault on bus, and in the options we have to select all buses. As we have to conduct three-phase to ground fault on all buses, we have to select all buses from the options. Now click OK, click on execute. Do you want to consider breaker capacity for cable lines? No. Then click on report, select standard, click OK. Similar to load flow analysis, it is showing what is the bus details and then two winding transformer data, transmission line data, generator data, load data. So these are all the data of the system. Then comes the output results. In this output results, case number 1, result for three-phase to ground fault on bus 1. So what is the fault current in terms of positive sequence, negative sequence and zero sequence, magnitude and angle, and then phase wise, A phase, B phase, C phase, magnitude and angle, and the fault MVA, positive sequence, negative sequence, zero sequence. These are in MVA and phase wise, A, B, C. A phase fault MVA, B phase fault MVA, C phase fault MVA. And it is also showing the R-base ratio, that is 0.05, then time constant, then P customary short circuit current. The post fault bus voltages, what is the voltage at different buses. So since it is a fault on bus number 1, we can see the bus voltage is 0 for the first bus, and it is showing the post fault voltage for bus number 2, bus number 3, bus number 4. Here this is the line to line magnitude, here it is phase wise, A phase, B phase, C phase voltage, and here it is positive sequence, negative sequence, zero sequence voltage. These are the magnitude and these are the angles. Then the fault contribution from two winding transformer, then fault contribution from transmission line, then fault contribution from generator. Actually, the fault is spread from the generator, which is going through the transformers and transmission line. So the fault contribution is 1312.1.6 from the grid 220 kV bus. Okay. So this is positive sequence current, this is negative sequence current, and this is zero sequence current, and this is the angle. Similarly, here also we can see phase ABC phase currents, and then ABC voltmeter. So these are the results for a three-phase to ground fault on bus number 1. Similarly, we can see the results for a three-phase fault on bus 2. What is the current in ampere and angle, and what is the fault MVA in magnitude, and then post-fault voltage for a fault on bus 2, and then what is the contribution from two winding transformer, from transmission line, and then what is the fault current and fault MVA for a fault on bus 3. So the fault current is 92741 positive sequence current, and fault MVA is 1766.97 for a fault on bus 3. Then post fault voltage for a fault on bus 3 and fault contribution. So similarly, if you show the results for three phase to ground fault on bus 4, post fault voltage, fault contribution, and then it shows the breaker sufficiency. Then it is showing the bus fault summary for bus 1, bus 2, bus 3. What is the rated voltage level, and then what is the fault MVA and fault current. Now we'll consider a case study, a three-phase to ground fault on planned 220 kV bus. Here the planned 220 kV bus is number 2. So short circuit analysis, that info, select three-phase to ground fault on bus, select in options. We have to click on selected bus because we are considering a fault on three-phase to ground fault on bus number 2. A particular bus we are considering, so we have to click selected buses from the options, and then double click on the bus number 2. When you double click on bus number 2, it will be displayed here. The bus which we have selected will come here. Then here we have SD dash, SD double dash. We have to select which reactance we have to consider for conducting the fault analysis. So usually for designing the circuit breaker, we use SD double dash, and then pre-fault voltage we can select flat start or input from load flow. So if we are considering the pre-fault voltage as 1 per unit for all buses, so we have to enter flat start voltage value as 1. And then whether do you want to consider induction motor contribution, synchronous motor contribution, cable or shunt capacitance, HVDC contribution. We don't have any of these elements anyway, so we can uncheck them. Short circuit output options. In the print option, we have data and results only. Then detailed print of data and results with Cartesian coordinates. So this is like the print options in the load flow. Data only will give only system data, results only will give only output results. Data and results will give both system data and results. Detailed print of data and results will give the Z bus. Then post fault voltage, whether you want to compute or not. If you want to compute, then you have to click on computed. for all buses or for selected buses. So if you are selecting computer for all buses, it will compute for all buses, and we have to select the unit per unit or kV. If you are selecting per unit, the voltage will be in per unit. Click OK, execute. Do you want to consider breaker capacity for cable lengths? No. Click on report, click OK, and then comes the results. So here, what is the fault current? It is showing 6286.858. This is the fault current. This is positive sequence current, negative sequence current, and zero sequence current, phase A current, phase B current, and phase C current. So these are the magnitudes, and this is the angle for A phase, B phase, C phase. Then fault MVA, you can see the positive sequence, negative sequence, and zero sequence fault MVA, and phase phase, A phase, B phase, C phase fault MVA. The peak arithmetical short circuit current is 15726.27. Then the post fault voltage. So here we can see the fault is on three phase fault is on bus 2. So you can see the voltage A phase, B phase, C phase voltage all are 0, and the voltage on bus number 1 is 0.678 per unit, and bus 3 0.43897, bus 4 0.67859. So these are the voltage, post fault voltage for different buses, bus number 1, 2, 3, and 4. And the fault contribution from two winding transformer. So we can see the contribution from the different transformers. We have 3 transformers, and the current sequence values like positive sequence, negative sequence, and zero sequence, magnitude and angle. This is in terms of phase wise, A phase, B phase, C phase, and fault MVA, A phase, B phase, C phase. There are 3 transformers. It is showing the fault contribution from either end, from primary and secondary, for all the 3 transformers. Then the contribution from transmission line from one front side and two side of first transmission line, and the front side and two side of the second transmission line. And here also we can see the positive sequence, negative sequence, and zero sequence current, magnitude and angle, phase wise, and fault MVA phase wise. Then the contribution from generator. The contribution from the generator is connected to bus number 3. It is 40649. From the grid 220 kV, it is 4243.733. Fault MVA contribution is 1617 from grid bus, and from generator bus it is 774.476 MVA. And the fault contribution from the load is 0. Then the breaker sufficiency. The fault is on bus number 2. We have breaker connected to transformer from side and line from side and two side. So it is showing the breaker flow, actual breaker flow, and the breaker rating which we have selected. The breaker is sufficient. Since the breaker flow is less than the breaker rating, we don't have to change the breaker. Then it is also showing the fault summary. What is the 3-phase MVA and 3-phase current for bus number 2. Now we will plot the results. For that, we have to click on plot short circuit study. If we want to see the summary, we have to check the summary like load flow analysis. We can set the precision here for bus display voltage. We can set the precision here. For power flow, we can set the precision here. Click OK. So here we can see the pole current at bus number 2. It is 6286.86. Now this is actually based on the selection what we are selecting here in the short circuit output options. We have selected plot option as phase A current, so it will display the fault current at bus number 2. Also it will display the contribution from the generator through the transformers and from the grid through the transmission lines. What is the contribution from the different elements? Then to plot AC current, what is the DC current and what is the total AC plus DC current at different times, we have to click on graph. Here we have to select x-axis and then double click on time in seconds. Then select y-axis, double click on AC current and then click on plot. It will show the AC current plot. Now to plot DC current, we can deselect AC current and double click on DC current and then click on plot. So it will show the DC current. What is the DC current at 103 seconds? How to know that? You can click on this graph and then click on view, then select trace and use this arrow. Enable this x-axis and y-axis grid lines and then click on view, select trace and then click on arrow. So it will display the current for time of 103 seconds. Then to plot AC and DC together, just double click on AC plus DC and then click on plot. So this is the AC plus DC current. So here we can see a subtraction period and then transition period and then steady state. Now to plot all these three AC current, DC current and AC plus DC for a voltage inception angle of 0 degree, double click on all these three and then click on plot. It will display what is the total AC plus DC current and then AC current and then the DC current. To save this image, we can click on file, save as image. You can select the extension and then you can give the file name and then click save. You can save in any drive and save. So it will be saved in the documents. Now we will conduct a single line to ground fault on generator bus. Click on solve, short circuit analysis, give a case number and then case name, and click on study info. Select single line to ground fault, fault on bus number 3, the generator bus. Click on close. Remove this plan 220 kV bus. To remove that, we can select this and click on delete flow. And then click OK, execute, report. The fault current is high, 117.851 kiloamps. So to limit this fault current, we can connect NGR, neutral grounding resistance or reactance. Double click on generator and then in the generator data, we have to enter the neutral grounding resistance. To limit the fault current to 100 ampere, we need to connect a neutral ground resistance of 63.5 ohm. How this is obtained is bus voltage is 11 kV. So the neutral ground resistance is equal to phase voltage divided by fault current. So phase voltage is 11,000 by root 3 divided by 100. 100 is the fault current to which we have to limit and then click on save. So short circuit analysis, select study info, click OK, execute, click on report. The fault current has been reduced to 0.1 kiloamps. It is nothing but 100 amps. Now what is the healthy phase voltage? The fault is on Generator terminal, the healthy phase voltage is 1.73 per unit. These are the healthy phase voltage. Now, for conducting a fault simulation, we can select any element. For example, this line. Select fault simulation, and we can enter the fault current 1000 ampere. So what is it for? So when I enter a fault current here, there will be a fault on this line at a distance of 50%. That is nothing but the fault is on the middle of this line, and the fault current is 1000 ampere. The fault type is 3-phase to ground. Then click OK. So there is a fault here, a 3-phase to ground fault, 1000 amps. It will display contribution from the grid and from the generator.
So concluding, so we have learned how to do fault analysis using MiPower, how to simulate different types of faults like 3-phase to ground fault, SLG fault, etc. And also we have seen the configuration settings and features in SCS. Thank you.